Hello, my name is Zoltan Stenovsky, and okay, thank you. So the topic of this talk is dust detection. I'm going to talk about the LDEX instrument for the LED emission, and I'm in a lucky position that I don't need to introduce you the LED emission because Rick Alfik did a marvelous job earlier today. And the LDEX instrument has a PI, Mihály Horányi. Myself, I am the instrument scientist, and there is a long list of collaborators and institutions who are involved in the development, including the Heidelberg dust group. Okay. So the science for LDEX is basically to characterize the dust environment of the moon. And we can think of two dust sources, two processes that can elevate dust from the lunar surface into higher altitudes. And these are the ejecta clouds generated by the continual micrometeorite bombardment of the lunar surface, and also possibly the electrostatic lofting of the lunar dust. This is due to the charging of the lunar surface. So there's a little bit of questionability of this process, whether this is the electrostatic lofting is happening. So I'm sure that you have seen these pictures before. So there are several optical and in situ observations that collectively led to the understanding or the suspicion that dust might be lofting from the lunar surface due to electrostatic charging. And these include the observation of the lunar horizon globe, and these also have been measured by high-flying aircraft, the paper by Lau and Brownlee from 1993, and modeled by the Grün model from 1985, I believe. So just from considering the geometry, about 5 tons per day of the same material is also hitting the lunar surface. And as you may expect, if you have an airless body, which is bombarded by very high velocity particles, then high velocity, I mean tens of kilometers per second, then an ejecta cloud is excavated. Basically, a crater is excavated from the surface, and this process has been observed in the Jupiter system. When Galileo has been making observations in the Jupiter system, it has encountered and passed by several of the icy moons, and then have experimentally observed that there is an enhancement of dust clouds. Basically, there's a dust cloud around all of these icy moons, and this is a dust which is originating from the surface, it's kicked out from the surface, and then it's returned back because they don't have enough escape velocity. So the similar process is probably happening, for sure is happening on the lunar surface. This picture here shows the measured radial distribution or number density of particles around the icy moons, and models exist to characterize the ejecta cloud, and the necessary parameters include the yield, which is basically a normalized mass, how much ejecta mass is kicked up by impacting dust particle, also the mass and the velocity distribution of these ejecta particles. So we actually know much less about ejecta cloud particles from the moon as a rocky surface, but if we assume some reasonable numbers for these parameters, then Mihály Horányi calculated an expected number density of dust particles as a function of, this is a function of radius, this is for a particular 50 kilometer altitude. And this dot here is an expected or an assumed density of dust particles that cause the excess solar brightness. So these figures show the number density as a function of altitude. So this is color-coded. The brighter the color, the more dust density. For an expected 30 by 100, this is an expected 30 by 100 elliptical orbit for the LEDI mission. So this is the dust that the LEDI spacecraft and the LDEX instrument is going to encounter. This is the impact rate. The impact rate is changing slightly because of the altitude is changing. So we have in the background, we have the ejecta cloud particles, which are always present. And then we assume that the lofty particles are mostly concentrated at the local sunrise and local sunset. So I'm sure you have seen this picture as well. This is to represent that or point out that the plasma environment of the moon is actually very dynamic and it's changing and it's very complex as well. So we have the sun and the solar UV radiation is driving most of the charging of the surface. So the exposed surface is charging positively, the dark side is charging negatively. We have a number of processes that really are happening, and now we have to add the dust coming off from the lunar surface as well, and these dust particles are charged in this environment and become a natural dusty plasma laboratory in the neighborhood of the moon, and also interact with this highly dynamic plasma environment. So we expect to see some temporal variability for the dust cloud around the moon. So first of all, we have the spherically symmetric, continually present ejecta cloud. This is due to the continual bombardment of the moon. But also, the mission is going to last for about 100 days. During those 100 days, we will surely encounter some of the meteoric showers. So these meteoric showers will introduce a spatial and temporal variability. So meteoric showers can last for a day or two, and they typically come from a certain direction. And then if we assume that the electrostatically lofty dust is actually happening, then of course we can expect variability with solar activity, because the sun is the major driver of the charging of the moon, and the fraction of the part of the solar spectrum which is responsible for the charging can be varied several fold during solar flare conditions. They can be increased by a factor of 5 or so during extreme solar flare conditions. And also we can expect variability with solar wind conditions, because these are both drivers of the charging of the lunar surface. But enough of the science, so let's take a look at the instrument. This is the LDEX instrument. The effective collective area is about 100 square centimeters. The instrument itself has been derived from previous successful dust instruments. The target is a hemisphere. This is the target. The ion collection is happening either on the target or in a microchannel plate placed here. The instrument has a deployable door, which is going to be only deployed or opened once LDEX is in orbit around the moon. And this is basically the operation. So an electric field is generated by this little hemisphere biased at minus 200 volts, which is collecting the ions. So an incoming dust particle generates an impact charge. Electrons, both electrons and ions. The electric field will separate them. The electrons go to the target and collect it there, and the ions go to the microchannel plate where the signal is amplified and measured. The total charge that the dust particle generates is proportional to the mass of the dust particle. This is how we can measure the mass. And there are two measurements that we do, one from the target and one from the microchannel plate, and both of them should measure the impact charge of the dust particle. So that's the measurements that we do. And as I mentioned earlier, there's also this expected or possible population of very small but also very abundant dust particles which are responsible for the excess brightness. These particles are much more difficult to detect individually because they are tiny. They are in the order of 100 nanometers or so. The charge that they generate by the impact is on the order of 100 electrons or even less. So they cannot be detected individually. However, what we do, or what we can do, is to measure them collectively. So we invented a new method of measurement where the dust particles are coming in, and we take the signal that comes to the microchannel plate, and then we integrate that signal for a short period. So we integrate the signal from hundreds of small particle impacts, and then we modeled how the signal might look like. Let's say that there is a ejecta cloud, or not an ejecta cloud, sorry, a lofted cloud at the terminator, and you are encountering the terminator. So this could be this is how the measured integrated signal will look like. Okay, if you're in a business of developing dust instrument, you better have an access or your own dust accelerator. And we have been lucky enough to have a very long and successful collaboration with the Heidelberg Dust Group. So we took the LDEX instrument and had 2 calibration campaigns so far in Heidelberg. And I'm lucky to report that the NASA Lunar Science has funded the development and construction of a new dust accelerator in Boulder. And about 2 weeks ago, we had the first testing of the LDEX instrument in this new facility. So I will not spend time here. So this is the calibration result. So what you see here is the total charge measured relative to the mass of the impactor as a function of the velocity. And the 2 colors represent the target signal and the microchannel plate signal. So those are basically the same measurements taken, except the microchannel plate signal is amplified by about a factor of 1,000 or so. And then we established an empirical relation between the charge and the mass of the particles. So just to summarize, the science for LDEX is the characterization of the dust around the moon, both the ejecta and then electrostatically lofted dust particles. The instrument is built at LASP, University of Colorado, and then now we have a calibration capability at the same institute. And the launch is in 2013, and the whole mission will last about 100 days. Thank you.
When you're in the integration mode, and you're looking at more than a few particles during this time, how do you distinguish between a few large particles and a great many small particles?
Yeah, that's a good question. So if I go back to this slide, so these spikes here, those are the large particles. So we can, but the large particles are identified individually. So we can always subtract them from this measurement. And then what you're really looking at is the bottom contour of this curve. So and that is the integrated charge. Not the spikes are the individual large particles. And that's how we can tell them apart.
Brian O'Brien, I'm wondering, one of the fascinating things would be to fly the equivalent of the lunar, the LEAM from Apollo 17 again, since it reportedly measured highly charged, slow dust particles. Now, I'm a little uncertain as to why the disconnect. You can only measure big, heavy dust particles individually, is that right?
Well,
could you measure with this the particles that they think cause LEAM to count?
So those particles are heavy and they're moving at a low velocity near the surface. So they will never make it up to the altitude where LDEX is going to operate. But incidentally, we are also developing a version of an updated LEAM instrument which is designed to operate on the lunar surface to measure the very slow and heavier highly charged particles.
Okay, great.
Okay, thank you.